Phase locked loop. PLL is a control system that generates an output signal whose phase is related to the phase of an input signal. It consists of an oscillator which generates a periodic signal. This signal is compared with the phase of the input signal and the oscillator is adjusted to keep the phases matched. PLL are widely used in radio, telecommunication and other electronic applications. It consists of 4 blocks: phase detector, low pass filter, amplifier and VCO. Phase detector is used to compare the input signal Vs and the output from VCO. Low pass filter filters out the high frequency from the input. Amplifier amplifies the error signal. VCO is a free running multivibrator which operates at a set frequency F0 called free running frequency. Frequency can be shifted to either side by applying a DC voltage control voltage VC, hence named voltage control oscillator. The input signal Vs of frequency Fs applied to PLL. The phase detector compares phase and frequency of incoming signal to that of the output V0 of VCO. VE is the error which is generated according to the difference in the input signal and output of VCO. Phase detector is a multiplier which produces Fs plus F0 and Fs minus F0 at its output. The high frequency Fs plus F0 is filtered out by low pass filter and Fs minus F0 is amplified and applied as control voltage at VCO. VC shifts VCO frequency in such a way to reduce the difference between Fs and F0. Once this action starts, say the signal is in capture range. VCO continues to change frequency till its output frequency is exactly same as the input. This circuit is then said to be locked. Once locked, PLL tracks the frequency changes of input signal. Therefore, PLL goes through 3 stages: free running, capture and locked. The low pass filter controls the capture range. Once locked, the filter no longer restricts the PLL. VCO can track signal well beyond the capture band.
Oscillator. This is the block diagram of voltage control oscillator. Voltage control oscillator is a free running multivibrator and operates at a set frequency called free running frequency. This frequency can be determined by external timing capacitor CT and the external resistor RT. Its output frequency can be controlled by a control voltage, so it is called a voltage control oscillator. In the figure, a timing capacitor CT is linearly charged or discharged by a constant current source or sink. The amount of current can be controlled by changing the voltage VC applied at the modulating input 5 or by changing the timing resistor RT. Voltage at pin 6 is maintained at the same voltage as that of pin 5. A small capacitor of 0.001 microfarad is connected across pin 5 and pin 6 to eliminate the possible oscillations. A voltage control oscillator is commonly used in converting low frequency signals into an audio frequency signals. The voltage across the capacitor CT is applied to the inverting input terminal of the Schmitt trigger via a buffer amplifier. The output voltage of Schmitt trigger swings between VCC and 0.5 VCC, that is, VCC is the upper cutoff limit and 0.5 VCC is the lower cutoff limit. So we will get a square wave output across the output of Schmitt trigger. Now the Schmitt trigger works upon the charging of capacitor from 0.25 VCC to 0.5 VCC. Now in this diagram we know that this is the voltage across capacitor, that it charges from 0.25 VCC to 0.5 VCC like that. So whenever the capacitor exceeds 0.5 VCC, the output of Schmitt trigger will come down to 0.5 VCC, and whenever the capacitor is discharged and its output voltage reaches up to 0.25 VCC, the Schmitt trigger output switches from 0.5 VCC to VCC. Now this square wave output from the Schmitt trigger, it is passed on to an inverting amplifier so that we will get the inverting output. So at the pin 3 we will be getting a square wave, and at pin 4 the output voltage across the capacitor, so we will get a triangular output voltage waveform. So we know that the total voltage across capacitor changes from 0.25 VCC to 0.5 VCC. So the total change in voltage, that will be delta V equal to 0.25 VCC. Capacitor charges with a constant current source, so we definitely know that I equal to C dV by dt, that we can write it as I is equal to C delta V by delta t, that is change in voltage by change in time. 3 start. So this is our CT. So we come to know that delta V by delta t equal to I by CT. In this we know that our change in voltage delta V is 0.25 VCC. So we will substitute that 0.25 VCC by delta t equal to I by CT. From this we can write the equation for the change in time that is required for the capacitor to charge from 0.25 VCC to 0.5 VCC. That will be equal to CT into 0.25 VCC divided by I. In this, the I is the charging current and VCC is the applied VCC to the IC. Now we know that the time period of triangular waveform, we got a triangular waveform like this. So its time period is capital T, that is equal to 2 times the change in time, that is delta T, that is to charge from 0.25 VCC to 0.5 VCC. So we know that our whole time period will be 2 into delta T. So we know that the output frequency is 1 by time period, that equal to 1 by 2 delta T. So it will become, so our equation will become I by 0.5 VCC into CT. And we know from that equation, right, the capacitor charges through the resistor RT. So our current I equal to VCC minus the control voltage. That is that we were telling that at pin 5 and 6 the voltage will be same. So from VCC the capacitor charges, the current will be VCC minus VC by RT. So VC is the voltage at the pin 5. So from this we will come to know that the output frequency equal to 2 into VCC minus the control voltage by CT RT into VCC. From this we are about to understand that by changing the control voltage we can change the frequency. Also by changing the capacitor, external capacitor CT or RT, we can vary the output frequency. And this is how the voltage control oscillator works. And this voltage control oscillator is used in our phase lock loop. And that's it.